So we have a solution here, and the solution is copper sulfate. So copper sulfate, if you took and dissolved a penny in acid, you might come up with copper sulfate. We then take and put one electrode in here, and this electrode is just a sheet of copper. I could also pull out of my pocket, fish out a penny, and use that as the counter electrode. We're then going to take and put on my safety glasses because they're bifocals, not because they are so dangerous. But I have an electrode here, and the electrode right now is a little bit dirty, and part of that is it was put away without cleaning it last time. I'm looking for my tweezers. Take and dip it down into the solution just to kind of get it wet, and I want to clean off the electrode. Put that up there. Take a little bit of the paper towel. I'm going to wipe it off. Okay, so normal nanotechnology, you don't take and do something like that because you put so much contamination on. And here, because the surface is made of diamond, we can take and wipe off or braid off most of the dirt that's on there. If there's still any dirt there, we could take and throw it in concentrated sulfuric acid, concentrated nitric acid. We eat the hell out of everything that doesn't belong there. And we're back to the same pristine condition that it was when it was in the multi-million-dollar clean room. So I'm going to take and just attach that on there. There's a little clip. And I just make sure that it has good connection there. I'm going to stick that down into the solution. You just have to take and make sure that the clip doesn't touch. And right now there's 456 people in the world, or 455 people in the world that have done this. And I promised you that you could be 456. So I just want you to flip up the switch there. Okay, electrons are traveling down through there. They're hopping onto the ions floating around in solution. We already have nanowires, but we can't characterize nanowires unless we go over to the biology building there. So we're going to take and let this grow for an additional 30 to 60 seconds, at which point they're going to be somewhere in about the 3 to 5 micron range, roughly the diameter of a spider web. Spider web is something that we can see with the naked eye if it has enough dimension in one direction. We're going to take and we can certainly see a spider web with a microscope. So in the last few years, we've been able to take and have the electronics developed to the point where this is a microscope. There's a little camera in here and a little tiny lens at the one end. It makes a very simplistic but very effective microscope. And we have the computing technology now to be able to attach that microscope there. And I'm hoping the battery isn't dead. Should have planned for this. Okay, plan B. Plug it in. Okay, so we'll let that boot there for a second. At this point, we take and turn that off. Lift this out of solution, and you can see that you've done something. gosh, that whole square area used to be this dark gray, and now it's slightly coppery color. So I'm going to use that. I've got a little bit of glass right there, and that just gives me a nice flat area. And I was not turning on before, but here we have a microscope. And this microscope is amazingly powerful. And the hardest thing to do is to focus it. And so here's 400,000 copper stars that were not there just a few minutes ago. You took and made those. I mean, that's really how simple the technique is in order to be able to take and create that.
Why stars? Why that shape?
It's a cool shape. It's patriotic.
Right.
It's fun. It's also five-fold symmetry. And five-fold symmetry is something that doesn't occur in nature. So there's other kind of cool ways that we could take and make six-fold symmetry or triangles or squares or straight lines. But if we want five-fold symmetry, we've got to go through active patterning. Okay, and this means that if you're going to take and do it on that size scale, you have to have a clean room. There's no way around it, and because it's not something that there's any little cool trick of nature to be able to get something like that. So now we're going to take a piece of Scotch tape and put that over the top there. And I've pulled off most of those wires. In fact, we can take now and once again characterize this. And these here, what we're doing right here is micro technology. So there's your array of stars. It's not true nanotechnology because we can vision it with a microscope. But if we were to want to take and make true nanostructures, all we have to do is cut down the amount of time. We'd let it run for 5 seconds or 10 seconds. And we don't let it go for as long, and now students with a bare minimum of materials can actually take and do nanotechnology.
So the length of time allows it to grow larger? Is that
right?
Okay.
Right.
And how does that change their characteristics?
Well, the one thing is that you can see it. And that's probably the big thing. Now, if you were to take and try to image the nanowires, you might tell that there's something there that's scattering the light, but you wouldn't actually be able to tell that that's what you've set out to do. So now we've got this array of stars there. One of the ways that you can tell that you have there the registration between these has been preserved is you can take and shine a laser through there. So I'm going to take and shine a laser through there, and it's pretty pretty bright in the room. Let's see if I can kind of go over here. You notice that there's not just one dot, but multiple dots. If we, this is something I should really take in, but if you, but that pattern of dots that you get, if you were to take and throw mathematics at that, you could actually back calculate and figure out what is the shape that caused that spot pattern to occur. That spot pattern would essentially be back calculated into a pattern of stars like this. So there's a lot of potential for students to learn science and engineering through using relatively simple tools, and that's what I've developed is this NanoFab Lab in a box. And what we're doing with this NanoFab Lab in a box is they have the classroom activity of growing copper wires. Then they'll take and the classroom activity, everybody thinks, wow, this is really cool. And the fact that I'm number 456 out of 7 billion people in the world to take and do this, wow, that's pretty cool. But you know what? It's not my thing. And for the most part, we abandoned the 20% of the population of students that really get it and want more. We abandon them and don't take them any further than the bare fundamentals in a scientific concept because, well, 80% don't really get it and they don't care. And I'm saying that we're abandoning some of the best and brightest students from going further in a field, and we need to kind of catch them up. So.